Thank you very much, all of you, for joining. It's really a pleasure and an honor for me to serve as chair today. A few very quick words. Of course, I'll welcome you all to the Emmett Interdisciplinary Program in Environment and Resources, E-IPER, as you know. It is a pleasure today to serve as University Oral Chair for Andrew Hume's dissertation, which is titled Oceanic Influence and Sustainable Development of Large States. Now, we hope, and I'm sure you're all with me on this, that after Andrew's successful completion of these university oral exams, we'll formally award Andrew a doctoral degree in environmental resources. I'll just very quickly introduce myself. My name is Krish Sita. I'm a professor in the New School of Oceans with a joint position in environmental behavioral sciences, and still retaining a foothold in anthropology, which is my background. It's, of course, a pleasure to introduce two colleagues, but also who are serving as Andrew's advisors, Professor Rob Dunbar, co-advisor, and who's the William M. Keck Professor in the School of Earth Sciences, Professor of Oceans, of Earth System Science, and Senior Fellow at the Woods Institute for the Environment. And also Professor James Leape, another co-advisor, who's the William and Eva Price Senior Fellow, Woods Institute for the Environment, and co-director for the Center for Ocean Solutions. I'll just mention that we also have, very lucky to have Andrew's other oral examination committee members, Fiorenza Micheli, the David and Lucille Packard Professor of Marine Science, Chair of the Oceans Department, Senior Fellow at Woods Institute for the Environment, and by courtesy of Biology, and Kirsten Oleson, Professor of Ecological Economics, the Department of Natural Resources and Environmental Management, University of Hawaii. After all of those many, many titles, the pleasure is to introduce Andrew, who once he's finished, Andrew Hume, who once he's finished his presentation, you all as members of the audience will have a chance to pose your questions to him. I ask you very respectfully to please put those into the chat, and then I'll be able to moderate. And Andrew, of course, will be able to answer. Very great pleasure to hand over to Professor Rob Dunbar, who's going to make our gracious introduction to Andrew himself. Thank you, Rob.
Yeah, thanks, Krish, and thanks everyone for tuning in for this exciting event. We're actually gathered across the oceans for this PhD dissertation defense. Jim Leape's coming in to us from Bali, Indonesia, where it is 4 a.m. I think we could both give a protracted and well thought out introduction for Andrew, but I happen to have the better internet connection. And but Jim's gonna provide a few words after I'm done. So I'll go over a few of the basics here and tell you a little bit about how Andrew came to be at Stanford and how he's changed in his, at this point, significant career. So Andrew matriculated at Stanford in E-IPER in September 2017. So he's really finishing up in 5 years, which at Stanford, to have done so with COVID going on, I count as a real achievement, right? That through so many roadblocks that people, so congrats on that. Andrew came to us from the World Wildlife Fund, where he was directing an office of 10 people that were working on global and environmental facility funding. And that's where I first met him. I remember it was outside one of the Senate office buildings, beautiful sunny day, 2016, and I realized, he's dressed for working in Washington. He's got this crisp white shirt and a very nice tie, excellent slacks and shoes. And I looked down and I had the same outfit on. It was almost identical. And it hasn't happened since. I wish we had captured a photograph at that first meeting. But once I heard what he was interested in and about his background and kind of ocean science engineering and papers he'd written, I knew E-IPER was perfect for him, so I started putting the hard sell, you got to apply, and it all worked out. I should mention that before Andrew worked at WWF, he worked at the World Bank in DC also on JEF proposals and funding with a view towards ocean nations. So he was with the international development and finance world for about 8 years. Before that, he received a bachelor's and a master's degree in environmental science from the University of Virginia. And I've actually read his master's research publication on using engineering physics to make water column measurements of seawater metabolism, because that's stuff we still do in my lab, and it's quite a good paper. So at Stanford, as Jim knows, and many of Andrew's colleagues, Andrew's taken a somewhat winding path to get to his dissertation topics. He was intrigued by smart wind energy harvesting for poorer nations, and then using wind modeling and sensing to do so. He then became involved in a spectacular D-School project on the design of cheap and locally produced and scalable fish bags. These insulated bags that are designed to get fish to the market in really good shape and kind of transform the salability of fish for small-scale fishermen. Andrew took a number of trips to the Philippines and worked carefully with this crew, and others in that project have since created a real business that's going great guns there. But more recently, Andrew dove off the cliff into the big data world. And that includes data rescue and recovery, trying to find data, as well as unusual statistics and machine learning, some quite cool styles of processing that show up very clearly in the 3 chapters in his dissertation. So he taught himself a lot of new statistical and machine learning techniques, and produced the dissertation that you see before you. And while he was doing all of that, Andrew also worked closely with COS to write and successfully fund a $2 million Jeff proposal for Micronesia. And again, he's getting through in 5 years despite COVID. Andrew and I weathered COVID together at Stanford, and I greatly enjoyed our regular visits with our dogs and discussing science and next chapters over a beer. So thanks for that. Anyway, just kind of in a nutshell, I'm super impressed with this body of work because it shows a very new and different way forward for nations that have limited resources, perhaps small populations, perhaps very small land areas, but have large ocean areas to control. And so it's really quite new from that standpoint, and we're all going to enjoy hearing his summary of what he's done. Jim, would you like to say a few words?
Thanks, Rob. If connections allow, first of all, thank you for that really wonderful introduction for the great story of this journey that we've had together with Andrew over the last 5 years. Let me just add a couple things. I mean, as you've noted, Andrew came to Stanford. Well, first, he came from WWF, so we were off to a good start together. But he came, as you said, with a lot of experience in the worlds of development and conservation and a deep understanding for how all of that works and how it could work better. And you combine that with this driving passion for oceans and for helping the communities who depend on them, especially in small island states, was just a fantastic beginning. Now, I should note first that made him a real resource for all of us here who work on oceans. So from the beginning, he's been engaged with us in the Center for Ocean Solutions and others, helping us think about how to engage those communities and those issues. And as you said, Rob, not surprisingly, it also led to a lot of ideas and exploration. we did dig into several possibilities for what this work might be, but that's been a lot of fun. And the result is a really important set of pieces that help us understand some of the special challenges of large ocean states and can help development assistance better target those needs and help large ocean states thrive in a time of climate change. So I would just say Andrew's been a student for these 5 years, and that now comes to an end, but he's also been a wonderful colleague, and I am delighted that will continue for all of us going forward. And I look forward to the next hour and the hours that follow.
Thank you very much, both of you. Wonderful introductions and very heartfelt, clearly. Andrew, we hand over to you for your presentation, something that we're all very much looking forward to. Thank you, Andrew.
Great, thank you all. I'm going to share my screen here. All right, so thank you, everyone. Thank you, Krish. Thank you, Rob and Jim, for those very, very thoughtful introductions. I really appreciate it. And good afternoon, everyone. Good morning to some of you. I think we've got people calling Kirsten, Hawaii, Jim, Bali. think we have some people calling in from Denmark, Micronesia, and maybe even a few people from the climate COP in Egypt. And so I just really wanted to say thank you all so much to start this off. It really it's a big deal for me to present this, and I know it's not easy to take time out of your busy schedule. So just thank you all. So let's go ahead and jump in. As you know, my name is Andrew Hume, and I'm going to be presenting some of the highlights of my dissertation research to you today, titled Oceanic Influence and Sustainable Development of Large Ocean States. So to start, we're going to zoom all the way out, and we're going to talk about two of my favorite things, which, if it wasn't clear already, is international development and the oceans. And one way that these can intersect is through what's known as country classifications. So a country classification is a mechanism used by the international community to support countries facing a common development constraint. And I know this probably sounds like a pretty boring topic, but I promise you, they are really important. They're responsible for directing billions of dollars of international aid to specific countries addressing important issues from health to education to the environment. But before we go any farther, I should note that they have been criticized for perpetuating Western views of development, such as a deficit mindset that sometimes unfairly places the responsibility of addressing certain inequalities on developing countries. But there's over a dozen country classifications in use by organizations like the World Bank and the United Nations, and this widespread adoption demonstrates their usefulness. And as a focus of my research, classifications are defined using criteria that identifies groups of countries facing this common development constraints. Some examples of country classifications include the Least Developed Countries Classification, LDCs, Heavily Indebted Poor Countries, Fragile States, Landlocked Developing Countries, and as a big part of our discussion today, the Small Island Developing States Classification, also known as SIDS. So let's zoom in a little bit more and discuss one of the biggest advances in international development over the past several decades, and that's the adoption of the United Nations Sustainable Development Goals in 2015. So the Sustainable Development Goals, or SDGs, are a comprehensive set of 17 interlinked development goals addressing some of the most pressing issues of our time. And they're based on what's known as a triple bottom line conceptual framework, which tries to elevate social and environmental development objectives to that of traditional economic goals. And for countries that rely on ocean resources, this includes national policies and plans addressing several relevant SDGs, but most specifically SDG number 14, Life Below Water, which, as you can see here, aims to conserve and sustainably use the oceans, seas, marine resources for sustainable development. And as a demonstration of our country classifications in action, one of the targets under SDG 14, target 14.7, specifically identifies supporting small island developing states. So you can see here again, by aiming to increase their economic benefits from sustainable use of marine resources, including through sustainable management of fisheries, aquaculture, and tourism. But interestingly, over the same period, there's been a growing chorus of countries around the world referring to themselves not as small island developing states, but instead as large ocean states in similar terms. So for example, we can see here this quote made from the Marshall Islands to the UN General Assembly, where they assert that the Marshall Islands is a large ocean state. Our tuna fisheries resources represent a primary pathway to economic development, but our key stocks have been pushed beyond sustainable levels. And in fact, I was fortunate to hear the president of Palau refer to his country as a large ocean state while traveling across Micronesia in 2018. This large ocean state, or LOS phrasing, it got me thinking about this intersection of oceans and development, partly motivated by my own background working in marine science and environmental development before starting my PhD. And so this became the core motivation for my research. And so specifically, I was interested in answering the following three questions. So which countries are identifying as large ocean states and why? What influence does the ocean have on sustainable development? And how would a country classification support large ocean states? And so naturally, this led to the design of my dissertation, which consists of 3 chapters. So chapter 1, towards the ocean-based large ocean states country classification. Chapter 2, global fisheries and historic ocean seasonality. And chapter 3, articulating a large ocean state country classification using machine learning. All right, so let's jump right into that first chapter. And this was published with a great group of co-authors that you can see here in the journal Marine Policy early last year. And again, this chapter aimed to investigate which countries are identifying as large ocean states and why. And so to do this, we first conducted a literature review on existing SIDS academic research, and then analyzed country classification policy documents and white papers. And then we enumerated the occurrences of countries self-identifying as large ocean states in official United Nations statements, and then conducted content analysis on these UN statements to get a better understanding for why. But first, let's talk a little bit more about the Small Island Developing States classification. Again, more commonly referred to by its acronym SIDS. You can see here on the left, one of the major UN agencies, UNDP, which defines SIDS as a distinct group of countries with unique social, environmental, and economic vulnerabilities due to their small size, remoteness, narrow resource and export base, and exposure from global environmental challenges. As you can see on this map here on the right from another UN agency, 58 countries are classified as SIDS, spanning all major all major ocean basins. But you may have also noticed two things here. I mentioned two different UN agencies. And in fact, unlike any other country classification, the unfortunate reality is that multiple UN agencies and other international organizations are managing their own SIDS classification, each with varying criteria and addressing different development priorities. So what we're looking at here is this bar graph is showing a confusing set of different lists of countries classified as SIDS, ranging anywhere from 28 countries to as many as 58 countries. And from an ocean development perspective, this isn't the only issue with the SIDS classification. But to understand why, we'll need to go back nearly 50 years. So the SIDS classification actually originated as a subgroup of the least developed countries classification, which was established in the early 1970s during a series of conferences on trade and development within the United Nations. And it was during these negotiations which were focused on supporting the poorest countries around the world by promoting domestic terrestrial activities like agriculture and manufacturing. And this is important because, as you can see in this box here, where is the earliest SIDS classification criteria, which was developed in 1974. And if you look closely, you can see it lacks any recognition of ocean-related priorities due to, again, to that trade and development focus that I mentioned earlier. And what's worse is when we compare this with more recent 2017 SIDS criteria from the same UN agency, you can see that it's remarkably unchanged. And what's worse is that this early SIDS criteria has become the basis for most SIDS classifications used today, seen here with another UN agency's 2019 SIDS criteria. And so what we learned from our analysis was that this lack of ocean-based criteria persists across most SIDS classifications in use now. And if you put this in even more practical terms, let's look at another key event that's also occurred during the last half century of using the SIDS classifications. So in 1982, the UN Convention of the Law of the Sea was established. And this led to the creation of exclusive economic zones, or EEZs. And so EEZs effectively expanded a country's national territory seaward up to 200 nautical miles from their coastline. And so for many small countries, establishing EEZs dramatically increased their total sovereign territory by orders of magnitude. So for example, if we take the sovereign territory of the Marshall Islands, you can see here, it went from less than 200 square kilometers of land, which are those little green circles of coral atolls, to nearly 2 million square kilometers when we factor in their EEZ. That's an area that's roughly the same size as Mexico. And so within that includes the sovereign access and management of all the ocean resources within it. But as we just noticed in the previous slide, SIDS classifications have remained largely unchanged since the 1970s. So there's never been any criteria integrating this massive natural resource base into current SIDS classifications. And these limitations with SIDS classifications have already had some real world implications. So to start, the UN has recently recommended that a single SIDS classification be established. And this should be based on a single set of criteria, a single list of countries, and focusing on a specific development issue. But unfortunately, little progress has been made on this yet. Donor countries and institutions have also become confused and frustrated, and this has the potential to influence billions of dollars that could be better coordinated and more efficiently invested towards targeted issues. This lack of targeted support is already beginning to threaten ocean health. So for example, you can see in these two news headlines here, for the governments of Palau and Kiribati, who recently established very large marine protected areas in their waters only a few years ago, but are now discussing reopening them to commercial fishing based on the challenges that they're facing, balancing competing ocean management priorities. And yet, as I noted earlier, amidst this context of limitations with SIDS classifications, there's been some countries that have started referring to themselves as large ocean states in similar terms. So we have another quote here from a Seychelles ambassador in 2014, where they say that our islands may be small in land area, but we morph into large ocean states when our exclusive economic zones are factored in. And what makes this interesting is that this framing does not refer to an existing country classification. No UN body or other organizations ever formally tried to classify countries based on their ocean development needs. Instead, large ocean state framing was coined by island countries. And as the name implies, and also as we can see in this quote, it's often been done in contrast to the SIDS classifications. So to understand which countries are doing this, we dug into the UN archives and counted all the countries that have self-identified as large ocean states in official United Nations settings. We also analyzed these UN statements for potential themes to better understand why. And what we found was 51 instances of at least 15 countries identifying as large ocean states in official UN settings since 2001. And what you can see here in this graph is that both the number of countries on the left y-axis, as well as the number of instances of them identifying as large ocean states on the right y-axis, have both been increasing over time. And this global map shows where all the countries that self-identify as large ocean states are located, which are the blue dots. And you can see they're all over the world, including the Pacific and Indian Ocean, as well as the Caribbean. And so when examining these 51 UN statements where countries self-identified as large ocean states, we observed several common themes, with references to ocean economy, ocean size, and climate change being among the most frequently cited. And so we grouped these into three categories: generally ocean economy, ocean context, and ocean management. So as a quick recap of what we've learned so far, we first learned that the Sustainable Development Goals, or SDGs, are an international community's top priority and heavily feature addressing oceans as well as supporting SIDS. And at the same time, we've learned that current SIDS classifications have limitations, such as outdated criteria without ocean-based metrics, such as integrating EEZs that dramatically expand their natural resource base. And last, at the same time, there's been at least 15 countries that have begun self-identifying as large ocean states, and often citing the importance of their ocean economy, ocean size, and ocean management. And so this led us to conclude that there's an important policy gap with existing country classifications. And then there's a real need for a new ocean-based country classification to support countries that disproportionately rely on the ocean for their sustainable development. So to illustrate a path forward in this paper, we've proposed three simple classification criteria based on our large ocean state themes. Starting with an ocean size criteria, we proposed a ratio of country EEZ surface area to land surface area, helping identify geographically small countries with large EEZs. For ocean economy, we estimated a country's ocean natural resources by using a standard UN statistical metric, percent GDP coming from agriculture, forestry, and fishing, and weighting this by an EEZ to land ratio. And this helped us effectively prioritize countries with fisheries and large ocean areas. And last, for ocean management, we developed a criteria that describes the potential for investing into ocean management, such as staffing or equipment, and based this on a country's GDP relative to its EEZ area. And this helped us estimate a maximum investment in management per square kilometer of ocean. So overall, this paper highlighted important limitations with current classifications, helped us document the emergence of large ocean states, and started a conversation to motivate future research. Specifically, we first identified limitations with the SIDS classification in supporting ocean development priorities, such as the SDGs. We observed at least 15 countries that have self-identified as large ocean states, often citing their ocean economy, ocean size, and ocean management. And at last, we illustrated the need for a new ocean-based large ocean state country classification to support countries that disproportionately rely on their ocean for sustainable development. So now let's move on and take a look a little bit deeper at one of the key sectors for many island nations, and that's fishing. For some countries, fishing can account for more than half of their GDP and a main source of protein to feed their population. It's a multi-billion-dollar industry that relies heavily on healthy oceans to thrive. But as we've noted before, our oceans are in trouble. In 2019, the Intergovernmental Panel on Climate Change, the IPCC, released a special report that summarized much of what we know about the oceans, the climate change's impact on the oceans. And as we can see in this figure here, it's not great. The oceans are getting warmer, more acidic, and holding less oxygen. And this is having a major impact on the world's fisheries. One recent estimate suggests that global fisheries could lose approximately $10 billion in annual revenue by 2050 if climate change continues unchecked. As we saw in Chapter 1, this could have a disproportionate impact on large ocean states. But these impacts aren't the same everywhere. this IPCC figure shows the future impacts to fisheries under moderate and high climate scenarios. And what we see is that warmer and lower latitude waters are expected to see declines in fisheries harvests, which is the red area in both of the maps. And colder and higher latitudes are expected to see increases, which is the blue area in both maps. And this is generally being called what's known as a tropicalization of fisheries, where warmer water species ranges are moving poleward to find more comfortable environments. But if you look a little bit closer at this figure, you'll see two things. First, much of this future modeling is in disagreement, especially in the developing world. And you can see that here in these gray hashed areas. And the second thing is that this latitudinal generalization that I just mentioned around fisheries impacts are not entirely consistent. Some of the projections do show fisheries in some high latitude locations potentially decreasing, and some lower latitude areas where harvest may be increasing in the future. So instead of looking at these latitudinal differences using these absolute temperature changes, we could look at relative changes. And there's one relative perspective that's not really been explored in global fisheries research before, and that's ocean seasonality. So here, ecological theory suggests that ecosystems that have evolved with low seasonal temperature variation are more sensitive to temperature shocks than ecosystems that have evolved with much higher temperature variation throughout the year. And so what makes this interesting is that the low seasonal variation doesn't just exist in tropical latitudes where you might normally think. As these two images show, you can see that different ecosystems can have similar temperature variation, such as in a higher polar latitude. So for example, that plus or minus 3 degrees Celsius that we can see in both of these figures, they could be around completely different mean temperature values, whether it's 28 degrees Celsius or 4 degrees Celsius. And so this ecological theory suggests that both ecosystems, or in our case, fisheries, might have similar sensitivity to changes in their normal seasonal patterns. So to explore this empirically, we compiled a large data set spanning from 1950 to 2018 for 187 countries. We used sea surface temperature, or SST data, coming from a gridded data product that interpolated satellite and in situ observations. And our fisheries data consisted of total reconstructed marine capture fisheries harvest from an excellent database developed by the Sea Around Us program at the University of British Columbia. We also used other oceanographic and social economic variables as well. And then we used R to wrangle this data with the primary focus on developing a fixed effects regression model that plausibly estimated the causal relationship between changes in ocean seasonality and fisheries harvests. And I'm not going to explain this equation in much detail, except to say that we use time invariant country fixed effects and time varying year fixed effects. And these help us control for possibly confounding variables that might also influence fisheries harvests, such as fishing effort, ecosystem productivity, or even things like El Nino. So to quantify ocean seasonality, we defined it using a standard deviation of 12 monthly observations of sea surface temperature within a country's exclusive economic zone, or EEZ. So first, we calculated the average monthly sea surface temperature for each country based on gridded observations falling within its exclusive economic zone. So you can see in the top left here, this is Iceland for 2 different months in the year 2000. And then we use this monthly values to calculate an annual standard deviation, where 1 unit of standard deviation described roughly 2/3 of the country's ocean temperature variation throughout that year. And so we did this for all years for all 187 countries. And what's important to remember here is that low ocean seasonality doesn't necessarily mean low temperature or colder environment. What it really means is that there's been low variation in temperature throughout the year. And also, because standard deviation describes variation relative to a mean value, this approach effectively decouples our analysis from longer-term ocean temperature trends. And you can see that decoupling a little bit better here. This figure shows global average trends in sea surface temperature, which is the red line, seasonality in the blue line, and fisheries harvest in black. And what we see is that since 1950, ocean waters have not only been warming due to climate change, which again is that red increasing line, but also that ocean seasonality, the blue line, has been increasing. And again, what this means is that we have seen variation in global ocean temperatures throughout the year have been getting larger. We can also see that on a year-to-year basis, sea surface temperatures and seasonalities have behaved quite differently with fisheries harvests. In fact, our fixed effects regression that I just mentioned exploits this annual variation at a country level by effectively comparing a country's fisheries harvest to itself. And if we look at the country level, we can see how ocean seasonality allows for this new perspective for modeling global fisheries harvests. So this figure shows how countries map with latitude, which is on the x-axis, based on their average annual ocean temperature, where the gray dots on the right y-axis, and then seasonality, which is the blue dots on the left y-axis. And what we see is that with the gray dots, which is ocean temperatures are roughly linear with latitude. And this makes sense, right? Water temperatures do get colder as you get closer to the poles. But with the blue dots, or seasonality, this isn't exactly the same. Here, countries at different latitudes could have quite similar ocean seasonality values. So for example, if we take Greenland and the Pacific island nation of Tokelau with completely different ocean ecosystems, they do have similar low ocean seasonality values. And so our ecological theories suggest that their fisheries harvests may also respond similarly to changes in seasonality. So with these insights on our data mine, let's move on to discussing our main model, which was estimating the global average effect of past changes in seasonality on fisheries harvests. And so this figure shows the main model's output, which was a statistically significant and nonlinear response. And to orient ourselves on the figure on the left axis, we've got percent change in fisheries. And on the x-axis, we've got our ocean seasonality. And so one easy way to read this is that on the left side of the model's peak, on the left side of the curve, rather, this describes fisheries responses in ecosystems with low ocean seasonality. And on the right side of the curve, this describes fisheries responses in ecosystems with higher ocean seasonality. And so overall, our model estimated that past 1 degree Celsius increase in ocean seasonality led to a roughly 12% increase in fisheries harvests in those ecosystems with low ocean seasonality. But if we take that same 1 degree Celsius increase for ecosystems with higher ocean seasonality, we see a 30% decrease in fisheries harvests. And this can be seen a little bit better by looking at specific country responses, which are represented here in vertical gray bars, which show where countries fall on the model based on their average annual ocean seasonality. And the thickness of the bars represents the variation in seasonality over the last 70 years. And so if we take Peru, which is near the peak of the curve and similar to the global average seasonality of around 2.2 degrees Celsius, we see that a decrease in ocean seasonality, meaning going to the left on the x-axis, estimated decline in Peru's annual fisheries harvest. But if we go right and up the model curve, or an increase in seasonality, we see that this led to a slight increase in Peru's fisheries harvest. And if we move a farther away from the model peak to countries like Greenland and Tokelau that we mentioned earlier, here we see that an increase in seasonality resulted in an increase in fisheries harvest. But if we go to the right of the model peak, countries like Uruguay or Sweden, the model estimates the opposite effect. So here, if we continue to increase seasonality, we would see a decrease in fisheries harvests. And this matches up closely with what the model data and what we see in the literature. So this figure shows Greenland's trends in annual ocean temperature for the hottest month, which is the dark red bar, and for the coldest month, which is the light red bar, as well as ocean seasonality, which is our blue bar, from 1950 again to 2018. And what we see is that waters are warming faster in Greenland during the hottest months compared to the colder months. This is likely driven by increasing number of days with ice-free days rather during the summers. And again, this is leading to an increase in ocean seasonality, that blue bar. And what our model estimates, as well as what the literature suggests, is that Greenland's total fisheries harvests have been increasing too, largely driven by an influx in migrating Atlantic cod and herring species. But in Tokelau, with, again, similar low ocean seasonality, what we see is actually seasonality, that blue bar, is now decreasing. So this has been driven by water during the coldest months, which is that light red bar, warming faster than the hottest months, which is the dark red bar. And so overall, the literature estimates, as well as our data, declines in fisheries harvests. And this has been largely driven by declining reef fish populations that have been unable to migrate elsewhere. And if we go to Sweden, where ocean seasonality is already quite high, we observe increasing seasonality trends, again, that blue bar. And our model, as well as the literature, report declining fisheries harvests here, especially herring, cod, and the European sprat. And so overall, what we found was that varying country seasonality, that it varies all over the world. And this can help us explain those nuances in fisheries responses that we saw in the earlier IPCC figure. So we also tested our model's robustness by rerunning it with controlling for key potentially confounding variables, such as fishing effort, GDP, species type, or El Nino. And this was to help confirm if the fixed effects were doing their job. And what we can see here with the respective dotted lines for these variables is that the alternative models were quite similar in terms of their response to the main model, which is that thick black line. And we also did this for quite a lot of other alternative versions, which I'm not going to name every one of them, but you can see them here with the dotted lines and the legend on the upper right. And so what this suggested overall was that our parsimonious main model, the one with only the country and year fixed effects, provided a robust global average estimate for how ocean seasonality has been affecting past fisheries harvests. So to wrap up this chapter, what we learned was first that global average fisheries are affected by changes in ocean seasonality, and that country seasonality trends are varying all over the world, and this can help us explain those varying impacts on climate change, varying impacts of climate change on fisheries harvests. We also showed through this empirical modeling how past impacts can help us, are an important tool rather for helping inform future modeling. Again, those gray shaded areas we saw in our IPCC figure from earlier. And lastly, we use 7 decades of data here, and this highlights the importance of long-term monitoring, especially in data-poor environments such as many developing countries, to help produce and estimate these fisheries responses. So overall, these results can help us understand the key vulnerability of countries that disproportionately rely on marine fisheries resources for their sustainable development, including many large ocean states. So now let's move on to chapter 3. So this chapter built on the insights and the data from the first 2 chapters to articulate a large ocean state country classification using machine learning. And to do this, we employed a series of unsupervised machine learning processes. And by unsupervised, what I really mean is employing algorithms that learn patterns from unlabeled data. Or to put it even more simple terms for our purposes, this essentially meant organizing countries into similar groups with the goal of using a data-driven and transparent process to identify large ocean states. So more specifically, our workload for this chapter involved first identifying a large ocean state development constraint and then defining that with data. And then we ran principal component analysis, PCA, to extract underlying dataset variation, and then clustered using that PCA output using k-means and partition around medoids clustering methods. And from this, we identified a large ocean state cluster and used this as basis for membership in a large ocean state, a new large ocean state country classification that we're proposing. And then lastly, we analyzed the uniqueness of this large ocean state cluster to help us answer our motivating question, which you can see here, was how is a new country classification how would it best support large ocean states? So I know that was a lot. We're going to jump into those now in the next few slides. So first, let's discuss how the large ocean state development constraint was identified. If you remember from the beginning of the talk, we talked about how classifications support groups of countries based on a common development constraint. And by constraint, what we really mean here is a barrier or issue that countries face preventing development progress. And to do this for large ocean states, we built on the themes from chapter 1 related to ocean economy, ocean context, and ocean management. And specifically, our research identified that the challenges large ocean states face is managing exceptionally large ocean areas with limited management resources. So we named this the Large Ocean Limited Resource Development Constraint, or LOLAR for short, which, yes, I know is not a great acronym, but it represents a unique challenge for large ocean states to disproportionately rely on the ocean for their sustainable development. So some examples of the LOLAR development constraint include the challenges of having small fleets and staff that are tasked with monitoring and preventing illegal fishing activity within exceptionally large EEZs. Or if you remember from earlier, the potential reopening of very large marine protected areas in countries like Palau and Kiribati, based on the challenges that they face managing competing ocean economic and ocean conservation goals. So with the LOLAR development constraint identified, we next defined it with data using country average values for 18 variables across our 3 large ocean state themes, which you can see here in this table. We also refined our analysis down from 151 developing countries, down from 187 countries from chapter 2 to 151 developing countries, which are eligible to receive funding from a major environmental development fund, the Global Environment Facility, or GEF, which is also where I'm currently working. And so this resulted in a rather unwieldy multi-dimensional data set. And so to make this more manageable, but also to remove potential correlation among the variables that would influence our clustering, we used R-mode principal component analysis, or PCA. And so PCA essentially transforms the data set into a new coordinate system that describes the underlying variation with fewer and uncorrelated variables called principal components. And so this figure here shows our original data set that's been transformed for the first 2 principal components, PC1 and PC2. And so now we've got 2 uncorrelated variables that are describing most of the variation from our original 18 variable data set. PCA is also useful for helping to explore the most influential variables in the data set. And so what we can see here is with the length of the blue arrows, which is explaining loading or influence, we can see that the shipping, fisheries, tourism, and GDP variables are among the most influential in our data set. And this aligns nicely with the ocean economy theme that we've identified from earlier. So next, we use the PCA output to cluster our countries. And so without getting into too much detail on clustering, it essentially iteratively groups objects, or in our case, countries, based on similar characteristics using a predefined number of groups. And so what we can see here from these two figures is that on the left, we use the k-means clustering method, and on the right, we use partitioner-ametoids clustering. And we identified a large ocean state cluster, which is seen in blue, the ovals in blue, by identifying the cluster that included countries like Kiribati and Palau, which, as we noted earlier from chapter 1, are countries that are frequently self-identifying as large ocean states. And as we also identified for Palau and Kiribati, are countries that are actively facing this low LAR development constraint. And so while both clustering methods they returned similar results, the PAM clustering method was the better approach for our goal because it's much better at handling outlier data, which is essentially what we're trying to do by identifying countries that are most disproportionately affected by the low LAR development constraint. So as you can see in this map here, PAM clustering, the results from the PAM clustering identified 17 countries as large ocean states, which are seen as the blue dots, as well as the shaded blue areas as their EZs. And the name of all 17 are at the bottom of the screen. And they're located in the Pacific, Indian Ocean, Atlantic Ocean, as well as the Caribbean. And so these 17 countries were then used as the basis for developing, used as the basis for membership in our new large ocean state country classification that we're proposing. But briefly, just to show, when we compare these 17 large ocean states from the PAM clustering with the countries we identified from chapter 1 that are self-identifying as large ocean states in official UN settings, we found that the vast majority are captured by the PAM clustering. And so this helped us ground truth our results. Equally, we found that the 17 large ocean states are all part of 58 SIDS and one of the SIDS classifications identified by one of the major UN agencies. And this also highlights an important point that I wanted to make, which is that a large ocean state classification should aim to complement existing SIDS classifications, not try to compete with it in terms of funding or donor priorities. It could even be positioned within a subgroup of a future official UN SIDS classification if one ever comes to be. So to validate our clustering, as well as to help inform how the country classification would be best supportive, we compared the averages of the large ocean state cluster with the other PAM clusters based on our data set. And so, for example, what we see here is a large ocean state cluster, which is the blue bar on the top. We can see that they have the lowest average values for fishing harvests, which is on the left, tourism revenue in the center, and shipping activity on the right, compared to the other 4 clusters, C1, C2, C3, and C5, as well as when we compare all the countries together, which we label here as GEF for Global Environment Facility. But if we normalize these values to a country's GDP, so instead of fishing, we use fishing per nation's GDP or tourism per GDP or shipping per GDP, we immediately see that the large ocean state cluster now ranks the highest for all 3 variables. And even more compelling, if we compare the large ocean state cluster with commonly used SIDS classifications, we can see again that the average for the large ocean state cluster, the blue bar, is far and away the largest. And so these results quantifiably show how the large ocean state countries are disproportionately relying on the ocean for their sustainable development compared to their peers. And this uniqueness of the large ocean state cluster can also be seen across other key oceanic variables from the data set. So to start, we're looking at the large ocean state cluster here. They don't have the largest EEZ size, which is what we're looking at in this figure. That actually goes to cluster 5, which has countries like Indonesia, India, and Mexico. But when we compare it using the ocean to land ratio that we discussed in chapter 1, we can see now that the large ocean state cluster is far and away the largest. Large ocean states also have some of the lowest ocean seasonality, which if you remember from chapter 2, it suggests that they are highly sensitive to changes in ocean temperature variation. They also have some of the lowest average net primary productivity, or NPP, which is basically a measure of phytoplankton activity and is the basis for many marine ecosystem food webs, suggesting potentially low seafood harvests. And lastly, large ocean state countries are the most low-lying of all nations and have among the roughest sea states, shown here as significant wave height H sub S, which potentially shows their vulnerability to climate change. And from an ocean management perspective, large ocean states also have among the lowest total GDP and population size. These are actually metrics that are commonly used by the SIDS classifications to define what they call smallness. But for our purposes, it actually also demonstrates less financial and human resources for ocean management. We also have the lowest GDP per EEZ, which, if you recall from chapter 1, again, is a metric that we showed for representing the potential in investing in ocean management. From an ocean data perspective, large ocean states have among the largest total number of ocean observation platforms. But if we normalize this using the size of their EEZ, what we see is they have the smallest number of platforms per square kilometer of ocean. And so this highlights a potential limitation they face in terms of ocean data collection and monitoring to inform ocean management. And then lastly, large ocean states have among the lowest average score for marine protected area management. And this potentially shows a real world example of the LOLAR development constraint. So we've successfully identified large ocean states and a large ocean state country classification, but what's probably most important is how would this be implemented? This is most likely going to be done, this could be best be done rather, I should say, through financial and technical support. So on the financial side, this could include creating specialized funding sources that could invest into strengthening ocean management, such as vessel staffing and equipment, as well to help address issues like illegal fishing and managing these very large marine protected areas. The classification could also focus on de-risking and incentivizing private investment into small ocean economies, such as the tourism, fishing, and shipping sectors that I mentioned earlier. The classification could also help inform systems that are currently used to allocate funding to countries which are at the moment very heavily biased towards terrestrial ecosystems. And on the technical side, a large ocean state country classification could also provide large ocean states with access to technical data like geospatial imagery, software, and other specialized analysis and trainings. It could also help prioritize the global community to focus its ocean research, data collection, and long-term monitoring efforts into large ocean states, not only to improve the health of their oceans, but also global oceans. And maybe most importantly, new large ocean state country classification could help coordinate and focus existing ocean-based development efforts towards both a selection of countries, but also towards a specific development constraint like LOLAR that we mentioned. So in summary, in this chapter, we learned that the LOLAR development constraint is important for large ocean states, and that unsupervised machine learning on ocean-based criteria helped us identify 17 countries as large ocean states. And this was the basis for articulating a large ocean state country classification. We were able to quantifiably show how large ocean states disproportionately rely on the ocean for their sustainable development, and propose real-world solutions for how the international community could implement a large ocean state country classification. So we're nearing the end of my presentation now, and I hope we showed how important the ocean is for sustainable development, and that current classifications like SIDS classification have their limitations, such as a lack of ocean-based criteria. Our research identified 15 countries framing themselves as large ocean states and the context and characterizations for why, as well as highlighting the need for a new ocean-based country classification. We also established an empirical model showing how fisheries are affected by ocean seasonality and how this can help us understand the variability and vulnerability of countries, especially large ocean states. And ultimately, we identified 17 countries as large ocean states using this unsupervised machine learning process. And this demonstrated how they could be supported in a new large ocean state country classification to address the development constraints associated with managing very large ocean areas with limited resources. And the reality is we have less than a decade remaining to meet many of the milestones and targets of the Sustainable Development Goals. And unfortunately, nearly every country is woefully far behind. For large ocean states that disproportionately rely on the ocean for their sustainable development, the situation is not great. But as we've seen today, practical solutions do exist. We've provided evidence to strengthen the voice of large ocean states and propose ways to support them through a new ocean-based country classification. And hopefully, this can help ensure that they get the support they need to have a fighting chance, not only to meet their current needs, but also the needs of future generations. Thank you.
Excellent. I was trying to find a little symbol for the round of applause. Well done, Andrew. That was brilliant. Thank you very much. That really you've covered so much ground in that PhD. I'm just stalling slightly while I wait for questions. Okay, brilliant. So I sent through a little reminder to you all. If you have questions, please, by all means, send them through to the chat. In the meantime, perhaps if anybody on the panel might like to chip in with a quick question, you've got plenty of time afterwards. But would anybody like to step in while we wait for the audience to send through their questions? Then Andrew, if you don't mind, I might just start things off, if that's okay. You lay out really clearly the kind of, well, there's an interest to me because of the slightly kind of recent historic component to it. But these classifications, they really do seem to be sort of structural to the kind of perpetuation of ideas and inequalities and ideologies and so on, sort of just really built from, I know that many of these states that you're talking about have had a colonial context to them. What do you think about these classifications? What do you think might be a way to sort of change that dynamic? I mean, you've just shown brilliantly why it's important to look at those things. Can you offer comment?
Sure. Yeah, thank you. I mean, one of the ways to look at this, and I mentioned this at the beginning briefly, and something that I only unfortunately came across towards the end of my research, Kirsten brought this up, is this idea of a deficit mindset, which is one way in how many classifications and really development at large focuses on this idea of developing countries having a responsibility to fix some limitation that's imposed on them. But the reality is the large ocean state classification, one way of thinking of it is that countries are identifying themselves as this. It was not imposed on them by the development community. And in fact, they may be elevating and highlighting their own ocean resource potential and opportunities. And so one of the ways that this classification system could actually provide strengthening and basically focus the efforts of the development community by taking advantage of these opportunities. So instead of framing it as a limitation, looking at ways in which it can be used as an opportunity to elevate some of these social economic issues that we see, or some of the issues, again, is not the right word, but bringing it back towards an equality question. So I think that's certainly something that future research could address. And if I had more time, I would love to dig in more.
Yeah, excellent. Andrew, I'll sort of follow up with you at another time, if that's okay. You really brought a lot of things to my mind. If it's okay, I'm going to quickly repeat. Theo, of course, congratulates you on the excellent work and presentation. And Theo would like to ask you, how is vulnerability, for example, to climate change taken into account in LOS classifications?
Yeah, that's a great question. Thank you, Theo. So in the third chapter, we did present a few slides showing some of the data, and there's a lot more behind that, showing ways in which they're more vulnerable in terms of, for example, they have the lowest for sea in terms of elevation, so they're most vulnerable to sea level rise. The ideas around ocean seasonality, so changes in seasonality, they show that they may be most sensitive, so that would impact their fisheries. There's quite a few ways. And we could even take it back a step further to look at how we define vulnerability, which is in many ways one of the key characteristics used to define the SIDS classifications. So it's an area that we could dig in several different directions, depending on how we want us to look at the data. But I think there's a lot of different questions that we could dig in there. And we could hopefully talk about it more during the closed door session too.
Excellent. Thank you, Theo, for the question, and Andrew for the reply. I've got one from Nathan. Andrew, great job with regards to chapter 2. Curious if you can predict which countries will be most affected in future years from temporary seasonality changes. Nathan apologizes if he missed something from the presentation and just wonders if you've got any ideas of the effect on GDP.
From a GDP perspective, yeah. So thanks, Nathan, for the question. There's actually a new version of the data set that the Sea Around Us program is working on that's trying to better estimate GDP impacts. The current version that we're working with essentially has a almost consistent variable transition from fisheries harvest to national GDP. So we could almost replace fisheries harvest for fisheries value. And in fact, that's what we do in chapter 3. For a one-for-one change. And so when we talk about the potential sensitivity of countries to fisheries in terms of total harvest, we could almost replace it with sensitivity for GDP. And as we noted, that could be looked at from a sensitivity based on changes in seasonality. So small countries with little seasonal change are more potentially sensitive to any changes in that seasonality. So that could be the lower latitude and higher latitude systems. But we could also look at it from a perspective of the amount of value that a country gets in terms of its fisheries, whether that's percent GDP. So a country that heavily relies on fisheries for their GDP, if there was sensitivity to that fisheries harvest overall, that could have a disproportionate impact on their overall GDP as well.
Thanks, Nathan and Andrew, for the response. One from Jose, who congratulates you for the great presentation, Andrew, Jose Ortega. Can you discuss a little bit of the challenges and opportunities you see ahead for the adoption of this classification system by the international development agencies? Thanks, Andrew.
Yeah, and thanks, Jose. It's a great question. I mean, I don't present it here because it's somewhat of it detracts from my argument, but there is quite a large audience that says we have enough country classifications out there and don't need more. So it is quite a challenge. It's something that should be recognized to propose new ways of working. I think what I try to show in my research is that the current models that we have with the SIDS classification are due for changes. And in fact, the UN recommends that these changes should happen. And so whether or not that focuses on ocean priorities or not, that's a bigger question to have. But we can't ignore the fact that the development community at large has taken a larger focus on ocean priorities moving forward, whether that's through the SDGs or even many more recent things that we know about. I mean, Jim's in Bali and can probably comment on this better than I could. So I think there's many ways in which the adoption could move forward, but what's most important is to recognize that development as a whole and sustainable development especially are prioritizing the ocean. And so having a lack of focus on support towards that, depending on the development issue, is a big gap in how we move forward. So, I mean, the most simple way would be for an agency, a UN agency or a World Bank system to adopt a classification and then apply the series of proposals I have here for helping allocate funding. That would be the most simple move forward.
Excellent. Thank you, Andrew. Thanks, Jose, for the question. Any others? At the moment, we're just waiting for questions to come through on Q&A from the audience, perhaps. But if anybody from the panel would like to jump back in. Sorry, I'm reading something from...
I'm happy to jump in and ask a quick one, if I may. I love the clustering approach, and in our private session, I'll ask you a few things about R mode and Q mode PCA, but it's interesting that the PAM and the k-means methods, gave you these clusters that had a lot of similarity, even though they work slightly differently. And of course, the singular result to focus on is the large ocean states, but maybe a quick answer to possible ways to use the other clusters.
No, it's a great question, Rob. And I think we are clustering based on the LOLAR development constraint in this sense. So another way to look at this is that we could have a cluster that's most affected by this development constraint, as well as countries that are least affected by it, right? So that could be if you noticed, I mentioned this cluster 5 that has extremely large countries in it, like India, Mexico, and China. And that's true for a lot of development constraints. They're done based on a spectrum, not necessarily just a singling out of specific countries. So we could look at ways in which the other clusters are sensitive in other ways, or we could apply different data to, or even a different development constraint and apply those clustering methods to highlight various sensitivities. So that's certainly an approach. For those that have done clustering before, it's important to know how sensitive the results are depending on the input data, which is partly one of the advantages of using this principal component approach, because you're providing a combined set of variables versus individual variables. But you certainly could find different ways in which the results in different clusters come out that would prioritize. I know I have a few more seconds, but just as example, various versions of the clustering results didn't include Palau, for example, and Palau is sometimes an outlier among its peers because it has an extremely strong tourism base, generally speaking, not over the last couple of years. And in many ways, it's identified as a middle income country and outside of a lot of other classification support because of its economic situation.
Excellent. Thank you very much, Andrew, Rob, and all the questions that we've had. Before we move to the closed session, I'll ask Andrew if you would be kind enough to wrap us up and give you the floor for the last few minutes.
Great. Let me just quickly jump to my acknowledgement slide. So just quickly, I want to acknowledge funding. It's probably the most important thing, and I received a lot of financial support that's really important to recognize. Of course, E-IPER, McGee Leverson, the Stanford Center for Ocean Solutions, and the Richard Kaufman and Ellen Jewett Fellowship. So thank you for all of that financial support. Without that, I would not be here today. Of course, my co-advisors, Jim Leape and Rob Dunbar, thank you guys so much for being so supportive since day one, even if that meant indulging some of my crazy wind ideas, which I still think are valid and should be explored. To the rest of my committee, Fio and Kirsten and Gracious Chair, thank you all so much for your thoughtful comments and willing to just support me through this and make it all possible. For E-IPER, Anne-Marie, Gabby, and Sue, and even Suki, none of this could have happened without your untiring help and wavering commitment towards the E-IPER for making it such an amazing community. So just thank you. My cohort, Rebecca, Lynn, Joshina, Caroline, Randall, thank you all for keeping me on track and motivated. Center for Ocean Solutions, it's a second home for me, and Eric, Colette, Liz, Diana, Lynn, thank you all for agreeing to do a Jeff project with me without much more than just blind faith that it would work. Fortuna, my colleagues with the design class, David, Tamara, Michelle, thank you guys for basically making the non-research side of my experience at Stanford so incredible. Emily at the Hume Writing Center, Emily Polk, I can't thank you enough for just getting me on track at the beginning and making all this happen. Without having you, I probably would not have had the ability to write everything down. My family, my mom, my dad, who unfortunately is no longer with us, my brothers, nephew, my soon-to-be niece. Thank you guys for just years of support and inspiration and love. And of course, my amazing fiance, Amelia, hopefully she's still on. I know she's having to commute home in a few minutes, but none of this would be possible without you. I love you so much. And lastly, friends and colleagues around the world. None of this, I wouldn't be aware of these topics without just the incredible hospitality and just kindness of so many amazing people I've met, colleagues and friends every corner of the earth. And so to all of you, just thank you so much. This has been a humbling experience and I'm just truly grateful. So thank you all.